Welcome back. In this video, we continue our study of Chapter 1, and we move to Section 1.2 about the Stone-Weierstrass theorem. Okay, the Stone-Weierstrass theorem is an extension, a generalization of the classical Weierstrass theorem, which states that we can approximate uniformly a continuous function on a closed bounded subset by polynomials. Okay, so the Stone-Weierstrass theorem is in the same spirit, but is more general in the sense that instead of working on a closed bounded subset of Rn, let us say, we can work on any compact metric space, and we can approximate continuous functions uniformly because we put on CXR, as you know, the supremum norm or the norm of uniform convergence, and we will put conditions under which we can approximate such functions by better functions in a subset A. So this is, in other words, it's a density result, okay? Because density is basically an approximation. So this is the idea. We want to approximate continuous functions uniformly by better functions. Could be polynomial, could be C1 functions, could be Lipschitz functions. So this is the idea, okay? So in the proof of the theorem, that I will not give actually because it's a little bit lengthy, but it uses a very interesting theorem due to Dini. It tells us that under certain assumptions, pointwise convergence is uniform. Now, of course, uniform convergence implies pointwise convergence. The converse is not true, but sometimes if we put the right assumptions, we have the implication. So first of all, the first assumption is that we have to work on a compact metric space X, and the sequence Fn should be continuous and monotone. So we have something very specific here. So monotone means non-decreasing or non-increasing, and the limit must be also continuous. So under these assumptions, then convergence is actually uniform. So we need compactness, we need monotonicity, we need continuity of the sequence and continuity of the limit. Okay. So of course it's enough to prove the theorem for the case of a non-decreasing sequence, or increasing if you like. So this means that for every n and for every x, Fn of x is less or equal than Fn plus 1. Because if we prove the theorem for this case and we have a non-increasing sequence, then minus Fn is non-decreasing, and so we apply the theorem to minus Fn, and uniform if minus Fn converges to minus F uniformly, then Fn converges to F uniformly. So I'll prove it in the case where we have a non-decreasing sequence, and in this case we know that the limit is the supremum. Okay, so the limit is actually the supremum over n of Fn of x. Okay, now, so to prove uniform convergence, we give an arbitrary positive number epsilon. Okay, and we have to prove that starting from a certain rank and 0, independent on x, Fn of x minus f of x for all x is less than epsilon. So fix x, take an arbitrary x in this space. Now, pointwise convergence implies that there exists a positive integer n that depends on x and epsilon, of course. So I denote it by n of x, such that the distance between f of x and Fn of x is less than epsilon. But since f is bigger or equal than Fn, then the absolute value is just f of x minus Fn of x. Okay? So we can get rid of the absolute value because this is something positive. Okay, so to each x in x, we associate an integer n of x. Okay. Now, continuity of f sub n of x and the continuity of x, both at x, implies that there exists a positive number, alpha of x, such that if the distance between x and y is less than this positive number, alpha, that depends on x actually, then the distance between their images under Fn of x and the distance between the images under F are both less or equal than epsilon. Okay, so we combine the two. This is just continuity of, because here we are fixing x, and therefore we are fixing Fn of x. So this is just continuity of F and continuity of F sub n of x. Therefore, now so if the distance between x and y is less than alpha, then I use the triangle inequality. So f of y minus fn sub x of y, this is something positive because the limit is bigger because it's a supremum. So I introduce f of x and fn x of x. So if I apply the triangle inequality, I get that this quantity here is less than f of y minus f of x in absolute value, plus f of x minus fn x of x, plus the same thing minus fn of x of y. And now, according to so if you put everything together, the f of x minus f of y is, so the first term is less than epsilon. The second term is less than epsilon by this inequality, right? And this is something positive. I can drop the absolute value here. And the last term is less than epsilon by this inequality. Okay, so f of y minus f sub n of x of y is less than 3 epsilon, provided y is sufficiently close to x. Okay, and now I use compactness of x. It's clear that we can, if when x varies in capital X, then the collection of balls of center x and radius alpha of x covers x. So we can write x as a union of all these balls. Very trivial. How do I prove that? Double inclusion. Of course, each ball is in X because we live in the space X. And conversely, if we take, let us say, small a in X, then trivially, A is in the ball of center A and radius alpha A. So it's in some of these balls, and therefore it's in the union. So this is almost trivial. And compactness of X implies that we can cover the space X by finitely many such balls. Okay? This is compactness. And so I can take n0 to be the biggest among n of x1, n of x2, n of xm. Okay, this is a finite integer that does not depend on x anymore. Okay, and this will be the integer of uniform convergence. So if y is an x, then by this identity, x as a union of these balls, finite union of balls, then y is in some of these balls, of say of index j. So the distance from y to xj is less than alpha xj. Okay, so if now n is bigger or equal than n0, if we use this inequality here, 1, then we get f of y minus f of n of y is, of course, because the sequence is increasing, when n increases, the sequence becomes bigger. So f of nxj, since n is bigger than nxj because it's the maximum, then f of x and j is less or equal than f of n of y. So when the inverse, so minus fn of y is less or equal than minus fn of xj of y. So this is because the sequence is increasing. Okay, and if I apply 1, I get that this quantity is less than 3 epsilon, and that's it. So since epsilon was arbitrary, this means that fn converges to f uniformly, and this concludes the proof of the interesting Dini's theorem. Okay, so this is the first ingredient. In order to formulate the Stone-Weierstrass theorem, we need the concept of an algebra and the concept of a subalgebra that you probably know from other courses. Okay, so if you have a field K that we usually take to be just R or C, complex numbers, in algebra, calligraphic A over K is a vector space, first of all, over K, and it's moreover equipped with a multiplication that satisfies some required, some expected properties like distributivity, left distributivity, right distributivity, compatibility with scalar. So these three, actually, okay? So we have actually three operations on an algebra. The addition, which makes a group. We have multiplication by scalars with the usual property. And we have an internal composition law, if you like, that we call multiplication. So we have two internal or two composition laws. And they satisfy these compatibility conditions, okay, that we expect. Now, the multiplication need not be commutative, and I will give an example where it's not commutative, and examples where it is commutative. And as we expect, a unit of the algebra is the unit element for the multiplication. So, okay, so an element E is called a unit if EU equal UE equal U for every U in A. Okay, and if the multiplication is associative or commutative, which we didn't assume actually. So actually, if multiplication is associative, then A would become a ring actually. Okay. So we don't assume the existence of a unit element. We don't assume associativity. We don't assume commutativity. Okay. But some people, some authors include associativity in the definition. So, okay. Now, as usual, examples. Okay. If we consider the space of square matrices over the field K of size n by n, with the usual operations of addition, multiplication, and multiplication by scalars, then we get an algebra. Okay, because all the axioms of a vector space, of course, we know that from first year that it's a vector space, but if we combine addition and multiplication, we'll see that they satisfy these three requirements: distributivity, left distributivity, right distributivity, and compatibility with scalars. Okay, but as you know, this algebra is not commutative. It's associative because addition, multiplication is associative, but it's not commutative because AB is not BA when we multiply matrices. Okay, generally it's not commutative. And it has a unit actually. The unit is the identity matrix. Okay, second example, we take K equal R or C and X to be a topological space. And so this is very important. And you consider the space of all continuous functions from X to K, so from R to C. So R and C are both actually now not just fields, they are also topological space. So we can talk about continuity. So this is now a commutative algebra with unit or unitary algebra under the usual operations of additions of functions, multiplication of functions, and multiplication by scalar. Here, we have to have actually a field in order to define the multiplication of two functions. Okay. So, and of course, it's associative. So all the basic axioms are satisfied. And this would be our main example, actually, when working with an algebra. Okay. And by the way, what is the unit element here? It's the constant function, which is always equal to 1. Okay, this is the unit. Okay. Now, another example, if we have an open subset omega of the complex plane, and we consider the set of all holomorphic functions on omega, then with the usual addition and multiplication by scalars, then we get a commutative, associative, unitary algebra over the complex field. Okay, because why? Because the sum of two holomorphic functions is holomorphic, the product of two holomorphic functions is holomorphic, multiple of a holomorphic is holomorphic, and same thing. So now, a very important example, the set of polynomials over the field K is also a unitary algebra over K, because the sum of two polynomials is a polynomial, the product of two polynomials is a polynomial, multiple of polynomials is a polynomial. So, and if K is commutative, then this set of polynomials is also commutative, and of course associative. Okay, now subalgebra. If you have an algebra A over a field K, a subset B of A is called a subalgebra if it is itself an algebra under the same operations. Okay, and this happens if and only if B is stable under addition, under multiplication, and under multiplication by scalars. Okay, so we have two composition laws, or two binary operations, actually, as you call it, and one external operation. Okay, so as usual, examples. The set h of omega of all holomorphic functions of omega, as well as the set of all polynomials over omega, are both subalgebras of the algebra of continuous functions from omega to c. Okay, because they are stable under addition, multiplication by scalars. The set of polynomials over a subset E of Rn is also a subalgebra of the space of continuous functions, the algebra of continuous functions from E to R. Okay, the set of diagonal matrices is a subalgebra of F of MNK, which is the algebra of n by n matrices over K. Why is it a subalgebra? Because the sum of two diagonal matrices is diagonal, the product of two diagonal matrices is diagonal, multiple by a scalar of a diagonal matrix is diagonal. However, the set of symmetric matrices is a subspace of MNK, but it's not a subalgebra. I want you to think of it. Why is it? This is a counterexample. So not everything is a subalgebra. So it's a subspace, but it's not a subalgebra. You tell me why. Think of it a little bit. Why it's not? Which axiom or which property is not satisfied? Okay. Now, as you said, we will be interested in the algebra of all continuous functions from a compact metric space into R. This will be our main example. And of course, we equip it with the norm of uniform convergence, or the supremum norm, that makes it also a Banach space, actually. So we have so many structures on this important space. Okay? We have an algebraic structure, and you have a topological structure as well. So it's very important. So in addition to the usual properties of an algebra, we have the following properties. So first of all, since this set, so the space of continuous functions from X to R or to C, is also a commutative ring which is unitary. So it's a unitary commutative algebra and commutative ring as well. Okay, so and the norm of the product is less or equal than the product of the norms, and this is almost trivial. The map, so in words, if you like, multiplication is continuous. Here we can talk about continuity because we have a topological structure. So multiplication is continuous. Of course, addition is also continuous as well. And the closure of a subalgebra is also a subalgebra. Okay, so I think that A and B are just trivial. So to prove continuity of the map of the multiplication, since we are working in a metric space, so it's enough to prove sequential continuity. So take two sequences, Fn and Gn, converging uniformly to F and G, and we'll prove that Fn Gn converges to Fg, and for this we use a standard trick. We add and subtract Fgn and use the triangle inequality. So Fn Gn minus Fg in norm is less than the norm of Fn minus F times the norm of Gn times the norm plus the norm of F times the norm of Gn minus G. And since Fn converges to F uniformly, so in this norm, then this quantity tends to 0. But since Gn is convergent, then uniformly, then it's bounded. So this guy is bounded. So the first term tends to 0, and the second term tends to 0 as well. So we have just continuity of the multiplication. Now, the last term was somehow trivial as well. How do you prove that a bar is a subalgebra as well? We prove its stability under addition, multiplication, and multiplication by a scalar. So if we take two elements fg in a bar, then by the characterization of the closure of a set in a metric space, there exists a sequence fn in A converging to F and a sequence Gn of A converging to G. And since A is a subalgebra by assumption, then Fn plus Gn is in A. Okay? And since Fn plus Gn converges uniformly in the norm that we put on Cxk, then Fn plus Gn converges to F plus G, and therefore the limit must be in A bar. Okay? So this proves that A bar is stable under addition, and the proof is similar for multiplication by, so for multiplication and multiplication by a scale. Okay. Okay. Now, as we said, we want to give some sufficient conditions under which a subalgebra of Cxr is dense in C of X. This is the target. Okay. So one of these is, which is also necessarily, is the following one, is what we call the separation property of the subalgebra. So if you have a topological space X, which will take actually a metric space later, and you have a subset, not necessarily a subalgebra, just a subset of a collection of continuous functions from X to K. So we say that this collection separates the point of X, the points of X, if for every two distinct points X and Y in the space, we can find an element F in this collection such that F of X is different from F of Y. Or if you like, the other way around, the contraposition. If this happens whenever F of X equal F of Y for all F in A, then X equal Y, contraposition if you like. So same thing. So examples of separating collections. The collection of polynomials over R separates the points of R. Why? Just simply take the identity polynomial. But this is not the only choice. We can take t cubed. We can take any odd degree, because as long as it's injective, of course, you can take t cubed, t5. Okay. And more generally, the set of polynomials with n variables also separates the points of Rn. Same thing. Just take, for example, if X is different from Y, then at least some index X sub I is different from Y sub I, and we can take, for example, the projection map, actually, F of t equal Ti, if you like. And you can also, of course, invent other things. And of course, any subset containing a subset that separates the points of X also separates the points of X. Okay. So any set containing the polynomials is a separating set. Okay. And next result, which states that this separation property is necessary, actually. So if you have a compact metric space X and a subset A, which is dense in the uniform norm, then necessarily A separates the points of X. Okay. So this condition is necessary. How to prove that? We reason by contradiction. So what does it mean? It means that we can find two distinct points, X and Y, such that F of X equal F of Y for all F in the collection which is dense. And now consider the function from X to R, which is defined by G of t equal dx, the distance between X and t. As you probably know, this function is continuous. Actually, it's continuous in both variables. So in particular, it's continuous in t. So G belongs to Cxr, actually. Okay, and since A is dense, then there exists a sequence Fn in A converging to G uniformly. Okay, now since Fn is in A and f of x equal f of y for all f in A, then in particular Fn of x equal Fn of y. So since Fn converges uniformly to G, then in particular it converges pointwise. So at the limit we get g of x equal g of y because Fn of x converges to g of x and Fn of y converges to g of y. So you get g of x equal g of y. But g of x is 0 because this is the distance between x and x. And y is distance between x and y. Since x is different from y, then dxy is different from 0, but here it's equal to 0, so you get a contradiction. Okay, so this proves that if A is dense, then A separates the points of x. Okay, so this is one condition. But alone, this condition is not sufficient to guarantee the density of A. And here's an example. If we take in C01, so we just take x equals 0, 1, the space of continuous functions from 0, 1 to R, and we consider the subset of all continuous functions that vanish at 0. So f of 0 equals 0. Okay? Then, first of all, A is a closed subalgebra of A. So it cannot be dense, actually, but it's proper because A is different from. But as you may check, it's an algebra and it's closed. You tell me why it's closed. And it also separates the points of 0, 1. Okay? It's very easy because just take the identity. The identity vanishes at 0. Okay, so so we have now, so A separates the points of x, but A is not dense in C01. Okay, so the converse is not true. So we need something more. Okay, this extra condition is the following one. So that we need is that the algebra should contain, the subalgebra should contain the constant functions, or equivalently, the function which is always equal to 1. Okay. So saying that the calligraphic A contains the constant functions or contains the unit function is the same because the algebra, the subalgebra is stable under multiplication. Okay. So any constant function is actually a multiple of the one function, the unitary element. Okay. And now, having said all this, we can state the Stone-Weierstrass theorem. So we have a compact metric space X, and so suppose that the following go three properties actually. So first of all, A is a subalgebra. Second thing, A separates the points of X, and third property, it contains the constant function. If all these three conditions are satisfied, then calligraphic A is dense in CXR. Okay. Now, let me draw a corollary, which is, so the classical Weierstrass approximation theorem is a particular case of this general Stone-Weierstrass theorem when we take X to be a compact subset of Rn, and then any continuous function can be uniformly approximated by polynomials. Why this is a corollary of this? Because, and this is the meaning actually, so for every epsilon positive, there exists a polynomial whose distance to f is less than epsilon. Or if you like, in terms of sequences, there is a sequence of polynomials Pn converging to f. Same thing. Why this is true? Because if you consider the set of polynomials on X, then as we know, it's a subalgebra of CXR, as we showed. It contains the constant function, the constant polynomial, and of course, it separates the points of Rn, as you proved. So the classical Weierstrass approximation theorem is a particular case of the Stone-Weierstrass theorem. And final remark, the Stone-Weierstrass theorem does not hold when we replace R by C. And there's a counterexample in the exercises. We need something extra. In addition to the three conditions, we need the stability under conjugation of A. So when k equal R, this is automatic because everything is real. But when we work with C, this condition is not automatically satisfied. So we need this fourth extra condition in order to apply the Stone-Weierstrass theorem. Now, as I said, the proof of the Stone-Weierstrass theorem is a little bit lengthy. I divided it into 6 steps. It's not so difficult. You can understand it, actually. But in order to reduce the size of the video, and maybe most of you will not be interested. If you are really interested, actually, I suggest that you read the proof. It's in the notes, and it's clearly explained, actually. So I'll stop here, and in the next video, I'm going to solve some exercises about the Stone-Weierstrass theorem. So thank you for your attention, and see you next time.